Today, we're diving into a new AI-powered system that could totally change the game for maritime safety. It's built to answer one of the most terrifying questions you can face at sea. Is this ship actually going to sink? So, let's get into it.
Okay, just picture this for a second. You're on the bridge, alarms are screaming, the ship has been hit, and water is rushing in. Your crew, they're all looking at you, waiting for what might be the biggest call of their lives. Do you give the order to abandon ship, or do you fight to save it? Every single second matters, and you know the wrong choice could be an absolute catastrophe. In those moments of just pure chaos, the most valuable thing you have isn't courage. It's not even training. It's good, solid, actionable information. Knowing what's likely to happen next is the key. It's everything when you're making a life or death decision.
So yeah, this entire problem really boils down to making the best call possible under the worst circumstances imaginable. And the crucial piece of that puzzle is understanding the stability of your ship after it's been damaged. This quote from the research really gets right to the heart of it. Damage stability. It's not just some dry technical term for engineers. It's the science that literally determines whether people get to go home to their families. So how have crews been dealing with this until now? All right, so let's look at the traditional methods for a minute. And maybe more importantly, where they tend to fall short when a real crisis hits. For years, crews have had to rely on tools just like these. Pre-calculated paperwork, charts, and rulebooks. The whole idea is to have a plan ready for a bunch of different expected damage scenarios. But there's a huge fundamental weakness to this whole approach. Real-world accidents are, well, they're messy. They don't follow neat, tidy little rules. A static chart or a big binder full of plans can become almost useless when you're facing a bizarre, complex situation that's changing by the second. And this is just a perfect, tragic illustration of the problem. The Norwegian frigate Helge Ingstad sank back in 2018 after a collision. Now, the crew used their standard charts, but those charts assumed the damage was one single continuous hole. The actual damage was spread out, it was non-continuous, which was something the charts just couldn't model. And that led to a critical misjudgment. It's a textbook case of how rigid tools can fail in a dynamic disaster. So this is where the new approach comes in. Researchers basically decided to flip the whole problem on its head with a really clever breakthrough idea. What if, instead of fumbling around with charts and trying to run these insane calculations in the middle of a crisis, what if your computer could instantly tap into a massive digital memory, the experience of what happened in thousands of other similar incidents? And that is exactly what they built. Researchers created this enormous database by simulating over 2,500 unique damage scenarios. Each one of those simulations is a full story, from the moment of impact to the final outcome, whether the ship survived or not. This massive collection, well, that becomes the AI's life experience. This library of disasters, as I'm calling it, is the absolute key. It provides all the raw data for two different AI methods, and both of them are designed to make incredibly fast and accurate predictions. So let's dig into these two AI methods. They work pretty differently, but they both tap into that same powerful database to get to an answer. I love how this slide simplifies these two really cool approaches. Okay, so think of case-based reasoning, or CBR, as an expert detective. It takes the facts of your current situation and then searches its entire memory for the one case file that's the most similar, and it bases its prediction on that single best match. Machine learning, on the other hand, is more like a master pattern finder. It studies all 2,518 cases to learn the deep underlying patterns, the hidden rules of what leads to survival versus sinking. This flowchart here shows how it all fits together beautifully. On the right, you've got the CBR detective, and over on the left, the ML pattern finder. So when a real accident happens, all the data from sensors or from the crew comes pouring in. Both systems instantly go to work, they consult that central database of cases, and they deliver their prediction to a really simple dashboard for the crew. So let's just break down that CBR detective process a little more. It's actually pretty straightforward. First, it gets the data on the current damage. Then it searches that massive library for the most similar simulated accidents it can find. Third, it analyzes what happened in those past cases. And finally, it adapts that knowledge to spit out a clear prediction for the emergency you're in right now. It's simple, it's fast, and it's incredibly powerful. So this all sounds great in theory, right? But the only question that really matters is, does it actually work in practice? Let's take a look at the results. And the results are pretty darn impressive. the best machine learning model they tested was able to predict whether a ship would survive or capsize with 88% accuracy. I mean, just think about that. That's a remarkable level of certainty to have in your hands in a life or death situation.
And here's the other number that's just critical. The system can take in all that messy data from a real-time accident and deliver that 88% accurate prediction in just 10 seconds. In the time it takes you to just catch your breath, you can have a data-driven forecast of your ship's fate. That is a total game changer. And this wasn't some kind of a one-off fluke. This chart shows that several different machine learning models like AdaBoost and Random Forest, they all achieved really high accuracy scores. This just proves how robust the whole approach is. It's not just one lucky algorithm. The data itself is powerful enough to give you consistently strong results.
So, what's the big picture here? What does a technology like this really mean for the future of safety at sea? Well, ultimately, what this tech does is it transforms the pure chaos and uncertainty of an accident into clear, simple guidance. It gives crews the power to make the right call, backed by the experience of thousands of simulations. It gives them that absolutely vital window of time they need to plan a safe evacuation or a rescue. And maybe most importantly, it creates a kind of blueprint for how this idea could be used in so many other places. And that leaves you with this final, really fascinating question. If we can build a library of disasters for ships, what about for something like power grid failures? Or for building collapses, or even for financial market crashes? Where else could consulting a library of simulated catastrophes help us make better decisions today to prevent a disaster tomorrow?